Cambridge AS Computer Science, Chapter 1, Information Representation, Part 1. We start the AS Computer Science syllabus from the very beginning. Chapter 1 is almost or mostly copied from the O-level. So there aren't much new topics here in that chapter. Probably everything is repeated. It only differs in the level of details. It only differs in the level of complexity you have to deal with for the AS. Okay, so we start the AS with students who have studied the O level and did their best with the O level. So probably most of the topics here will be familiar for you. Okay, so let us start from the very beginning. Basics of number system. The point is, AS is explaining the same topics, but little bit much faster than it is in the O level. Okay, so you should have learned in the O level that we have a denary number system. That denary number system is based on base is base 10. We call it base 10 number system because there are 10 individual distinct symbols and digits available to express a number. So this is the denary number system, the numbering system that we are all familiar with. Okay, we did that in the O level. Okay, there is also binary number system that we call it base 2, and this is what we are here to study or already have studied. So with binary, the computer can only process data in binary form that are ones and zeros, only for the reason that because computers use logic gates, all of you already know what logic gates are, and also computers use switches and transistors that are either on or off. So the computer only uses binary number system. And this is what we are here to study. So the binary number system is base 2 system, which uses just two symbols, the 0 and 1. These binary digits usually referred to as bit. So what is a bit? Is a binary digit. All data inside a computer system are stored and manipulated using a binary code. However, it is better to use hexadecimal. I would rather use hexadecimal. So hexadecimal, it makes representing a binary number shorter. You already know hexadecimal from the O level. I'm just doing a start. Okay, so hexadecimal numbers are base 16. Okay, and therefore require 16 individual symbols. You already know that after the 9 you have A, B, C, D, E, F, and this represent 10, 11, 12, 13, 14, 15, up to 15. So 10 to F are digits from 10 A to F are from 10 to 15. Okay, you should be able to work out these examples really fast. Okay, so for example, a binary 0000 1000. If you'd like to change them into hexadecimal, you split them into two parts. Okay, so that 4 zeros will be represented here as 0. That 1000 is represented here as 8. This is hexadecimal. Okay, so the benefit of converting a binary number into hexadecimal, it is very easy to convert and to convert back, because you split the binary number into groups of 4, and then the weights become 1, 2, 4, 8, and that's it. And then again 1, 2, 3, 4, 8, and that's it. Okay, so this is a binary system. If you change it into denary, you put weights 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. I'm talking here about 8 bits register or 8 bits numbers. Okay, so you can easily convert the 000 into here 0 and 1010. So this is 8 and 2. You have to do that orally. We are doing AS right now. You have to be able to do that orally. So we have 1 and 2, and that is 10. You represent it here as A. Okay? If you convert the whole thing into denary, you get 10. So next, 0, 0, 0, 0, 1, 1, 1, 1. So it is 0F, because 1, 1, 1, 1 is 7. And I'm sorry, so 1, 1, 1, 1 is 1 plus 2 plus 4 plus 8. 8 plus 4 is 12. Okay, 12 plus 2 is 14. 14 plus 1 is 15. So F is 15. Okay, so 4 ones is just 15. And here it is F. And 1, 1, 1, 1, if you split it into two parts, this is going to be F and this is going to be F. So it is FF. However, if you put weights 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, you get 255. And this is the biggest denary number that can be stored in 8-bit register. So the beauty behind converting a binary number into hexadecimal, or the reason behind the easiness of converting a binary number into hexadecimal, is that you have to split it into two parts. And then headings become 1, 2, 4, 8, and this is one part. And the second part, you start all over again, and column headings become 1, 2, 4, 8. Okay? However, if you are converting a binary number into denary, you are not allowed to split. You cannot. And weights become 1, 2, 4, 8, 16, 32, 64, 128. If you have 8 bits here. Okay? And all of this is just revision of the O-level. Okay, let us carry on. Binary prefix and decimal prefix. This is also in the O-level. There is one little good thing that happened in 2023, is that they copied lots of contents from the AS and moved it into the O-level subject. So now I'm here teaching AS for students who did O-level and probably know most or all of chapter 1. Okay? So binary prefix, a kibi is 1024 bytes. So this is 1 byte. And a single bit is called a bit. Okay? 4 of them, we may call them a nibble. A nibble is 4 bits. Okay? Okay. Then we have kilo, mega, giga, and tera. But kilo is 1,000. Mega is 1,000, 1,000. That is 1 million. Giga is 1,000, 1,000, 1,000. Tera, you add extra 3 zeros. However, in the exam, probably they will talk to you about kibi. Kibi is not 1,000. Kibi is 1,024. Why? Because 1,000 is just a because in physics, kilogram is 1,000 gram. Here, the kilo is still the 1,000, and it is 10 to the power of 3. However, in computer science, because we rely deeply on number 2, so kibi is 2 to the power of 10, that is 1,024. Sometimes this makes calculation even simpler, because you have factors of 2 you can omit together. Everything in computer science is based on number 2. And then maybe 1,024 multiplied by 1,024. I don't think you have to memorize this. You have to memorize that kibi is 1,024. And then maybe 1,024 multiplied by 1,024. You don't need to memorize this because this is too complex. You have to deal with the fact that calculators are not allowed. So you have to train yourself to use paper and pencil in your calculations. I will train you about this. So maybe prefix represent the factor 2 to the power of 10. Kibi represent the factor 2 to the power of 10. Maybe represent the factor 2 to the power of 20. Gibi represent the factor 2 to the power of 30. Tibi represent the factor 2 to the power of 40. Okay? So it is about 2 to the power of 10, to the power of 20. To the power of 10 is 1024. To the power of 20 is 1024 multiplied by 1024. Okay. And let us look at the example. My notes is so full of examples. I have the hobby of copying past paper questions into my notes because I would like to train you as much as possible on exam questions. Okay, so once there was an example in the past paper, and also I like very recent questions. Okay, it says 1 terabyte is, and you have to complete, that is 1025 gigabytes. Okay, because the one TB byte, 1 TB byte is 1024 gigabyte, because this is on the binary prefix. Okay, however, 1 terabyte is only 1000 gigabyte, because this is the other scale. Okay, so one scale is the decimal prefix and the other scale is the binary prefix. Please get familiar with this, and please take your time and try to answer this. Okay, I will try to hide the answers from you. Okay, take your time and try to join these. Okay, thank you so much for your attempt. So 8 bits is just 1 byte. 800 bits, this is on the binary scale. So 800 bits is 1 kilobyte. Okay, 1000 kilo is 1 mega. 1240 maybe is 1 GB. 8192 bits. So probably this is 1024 multiplied by 8. So it is 1 kilobyte. Okay, thank you so much for your effort. Okay, let us move on, because in the AS we are going through the topics a little bit fast, because this is all repeated from the O level. Okay, let us recall binary addition, because that was on the O level. And then let us do binary subtraction, which is new to you, because you didn't do binary subtraction in the O level. Okay, let us do the binary addition. Okay, so the following binary addition. So you have this number plus this number. And maybe that's the reason why you are not allowed to use calculators, because calculators can add numbers in binary. Okay, so they cannot judge your skills then. Okay, let us start. 0 plus 1 is 1. Okay, 1 plus 1, that is 2. You cannot type 2. You cannot write 2 in binary. 2 is 1 0. So you already know from the O level that 1 plus 1 is 0 and carry 1. Okay? Okay, so now you will be adding 1 plus 0 plus 1. Again, this is 2 and that is 0 and carry 1. Here you are adding 1 plus 1 plus 0 and it is 0 and carry 1. And here you have 1 plus 0 plus 1 and it is 0 and carry 1. Here you have 1 plus 1 plus 1, that is 3. And this is 1 and carry 1. Here is 1 plus 0 plus 0, that is 1. 1 plus 0 plus 0, that is 1. And here there is no carry. And then 1 plus 0, and that is 1. And that's it exactly This is what you should do. Okay? Would you please give it a try solving this? Please give it a try and solve this yourself. Okay, thank you so much for your effort. Let us carefully recheck what you have done. So 0 plus 1 is 1. 1 plus 1 is 0 and carry 1. 1 plus 0 plus 1 is 0 and carry 1. 1 plus 1 plus 0 is 0 and carry 1. 1 plus 1 plus 1 is 1 and carry 1. 1 plus 0 plus 1 is 0 and carry 1. 1 plus 0 plus 1 is 0 and carry 1. Here we face a problem. 1 plus 1 plus 1 is 1 and carry 1. And carry 1. Okay, what's the problem about this? Because now I need 9 bits. The result cannot be stored in 8 bits. Probably because maybe the denary value of the result is something above 255. And we studied in the O-level that the largest denary value that can be represented in 8-bit is 255. And then you need an extra bit. Sometimes the system is not providing you with an extra bit. We call this overflow error. And most of you have noticed that. When we adding the above binary numbers, an error has occurred. This error is called overflow. The result cannot be represented in the current number of bits, currently 8. The result is a larger number that cannot be stored in the given number of bits. The result is something greater than 255. Okay? Okay, so that was a problem. Okay? Okay, that was a recall about what you have studied in the O-level. Okay? Okay? Now let us do binary subtraction. Now let us do binary subtraction. This is new to you because it wasn't on the O-level. So actually the point is, with addition you have carry. With subtraction you may have a borrow. With subtraction you may have a borrow. Let's go through it. Let's go through it carefully because this is new to you. Okay. 1 minus 0 is 1. Okay, that's so simple. 1 minus 0 is 1. That is so simple. 1 minus 1, that is 0. Okay. 1 minus 0 is 1. 0 minus 0 is 0. The problem is here. 0 minus 1. You cannot do that. You need to borrow. You need to borrow. So 0 minus 1, you cannot do. You need to borrow from here. Okay, that 1 becomes a 0. That 1 becomes a 0. And here it comes with a 2 and is written as 1, 0. So 2 minus 1 is 1. Okay? Okay. Remember that you have here a 0. You already now have a 0 because you have borrowed. Okay? So 0 minus 1, you cannot do that. You need to borrow. Okay? So this becomes a 0. And the one you borrow here, it becomes 1, 0. That is 2. So 2 minus 1 becomes 1. Okay, remember that you have here a 0. So 0 minus 0 is 0. 0 minus 0 is 0. Okay, this is the result. Okay? Okay? Okay, having done that, we have to look a little bit ahead. Because in the O-level, you already know what ones or twos complement is. And how can you represent negative numbers? Okay, because later on I will be teaching you representation of positive and negative numbers, And then there will be a more complex subtraction question. Let's keep this now. Let us keep this now, because in the future, there is going to be a more complex subtraction question. The complexity of it is that you are subtracting 127 from 12, and the result will be negative. Okay, let us keep that for later, because I would like to recall the 2's complement and the representation of negative numbers for you first, and then we do that additional subtraction question. Okay, so keep in mind that we will do binary subtraction again. Okay, let us keep recalling. Converting an integer value from one number base to another. So convert the denary value into binary. Okay, you may divide by 2. Okay, you already know that from the O level. Okay, but I'm not using that method of dividing by 2. I'm using the method of finding weights. Okay, so I think it is very easy for you to convert the denary number 246 into binary. So the binary equivalent of denary 246 is 11110. Okay, here I am representing the method of successive division. I don't like to use it. You would rather use the weights method. Already did that many times in the O level. Okay, now we come to hexadecimal. Convert the number 4e to denary. Let me explain one example for you, and you do the other. And as you can notice, that all of this is just recalling. Okay, so to convert the hexadecimal number, convert the hexadecimal number 4e to denary, we put the weights. Weights are 116 because this is hexadecimal. Okay, and the values are 4 and e. Remember that e is 14. Okay, so you have 4 by 16 plus e, that is 14, multiplied by 1, and you have to do that manually. You may not touch the calculator. Okay, so 4 by 16, this is 64, plus 14 by 1, and this is 14. So 64 plus 14 is 78. 4 plus 4 is 8. 6 plus 1 is 7. You have to learn or practice or remember how to add and subtract numbers manually. Okay, so that was an example about converting a hexadecimal number 4e into denary. Let us do the opposite. We would like to convert the denary number. 222 into hexadecimal. Probably we will be doing division, because here we did multiplication. Here probably we will be doing division. Okay, so you have 222, and your weights for hexadecimal are 116, 256. I hope that you will be only converting small numbers and you don't have to deal with the 256. In that example, we have 222, which is smaller than 256. So you need to put here a 0 and get rid of that. So how the 222 would fit here? How many times 222 goes into 16? You have to do long division. So 200, I'm writing this with my hands. Okay, so 222 divide 16. Let's go through it a bit by bit and see how you can do that in your exam accurately and fast. Okay, so first you take the 22. 22 divide 16, and that is 1. The 22 goes into 16 only once. Remember that from all days? Okay, so you put here 1. 1 multiply, we would like to find the remainder then. 1 multiplied by 16, and this is 16. And then you subtract. 22 minus 16, you get 6. Okay? And then you pull down the 2. So now you have 62. How many times the 62 goes into 16? You have to know the timetable, especially of that 16. So it goes 3 times. So you put here 3. 3 multiplied by 16, that is 48. And you subtract. Okay? 62 minus 48, you have to do borrow. 2 minus 8 is not possible. 12 minus 8 is 4. And now you have here 5. 5 minus 4 is 1. So 14 is the remainder. And 14 cannot be divided by 16 anymore. We cannot put decimal places. Okay? So 222 divided by 16 is 13 remainder 4. You put the 13 here, but it changes into D. You put the 13 here under the column weight 16. The quotient, the result of division goes here. However, you write it as D. Remember, A, B, C, D, E, F is 10, 11, 12, 13, 14, 15. Okay, so the 13 comes here as D, and the 14 goes here as 4. So it is 13, remainder 14. The 13 goes here as D, and the 14 goes here as 4. Okay, Shabab, was that easy? Can you do this yourself? Can you do this yourself? Convert the denary number 198 into hexadecimal. Do the division again. Do the division. You need to practice, because in the AS, they will be assuming that you are doing this really easily and not giving you plenty of time to do that. So you need to practice and train. And as you can see, we are not saying anything new up till now, except the binary subtraction. We didn't say anything new. I'm just training you about using AS questions. Okay, please go ahead. Okay, excellent, all of you. 198 divided by 16 is 12 remainder 6. The 12 goes here as 6 because it should be a single digit. Because if you write here 12, 1, 2, it may be considered that the 1 is here, and you should not. The 12 goes into here as 6. The C, I'm sorry. The 6 goes here into 6. Okay. Internal coding of numbers. Let me go through this a little bit fast, because all this is on the O level, the new O level syllabus. I'm happy with the new O level syllabus because it makes teaching AS easier. Okay, internal coding of numbers. A byte is a group of 8 bits treated as a single unit. The largest binary number that can be represented is 7 bits, is 2 to the power of 7 minus 1, which is 127. You can do this manually. If you have 7 bits, the largest value that can be stored in 7 bits is that one you fill here all with ones. So if you have 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, you do that. Check that yourself. You get 127. Okay? But we have a rule for it. And that rule will be used intensively in the AS. It is 2 to the power of 7 minus 1. I think for the AS, you should memorize all powers of 2. I know very well that 2 to the power of 8 is 256. So please know that 2 to the power of 7 is 128. 128 minus 1 is 127. Okay? So 8 bits. So this is, okay? So this is the largest value that can be stored in 7 bits. 8 bits can represent values from 0 to 2 to the power of 8 minus 1. Here you have 7 bits. Here you have 8 bits. So the range goes up to 255, which is 2 to the power of 8. 256 minus 1, that is 255. Okay? If the choice is to use 2 bytes, that is 16 bits, so values go up to the power of 16 minus 1, and this is exponential growth. 2 to the power of 16 is 265,536. This is 2 to the power of 16. I already memorized that. 2 to the power of 16 is 65,536. Minus 1, 2 to the power of 16 minus 1 is that figure. We will need to know that figure because you are all familiar with the O level. In the ASCII code, that only uses 8 bits, you can represent 256 characters. The Unicode, that is 16 bits, you can represent 65,536 characters. Okay? Okay. So that rule, 2 to the power of n minus 1, is here to stay, is here to be used many, many, many times. Okay? Okay, let us. Coding for integers. We did that in the O level. So this is just binary. Okay? And then signed integer. So that is positive and negative values. We did that in the O level. That is the 2's complement. Okay, let us revise. Okay, so coding for integer. Computer have to store integer values for a number of purposes. Sometimes the requirement is only for unsigned integer. Sometimes you are only dealing with positive numbers. So just don't bother yourself about being positive or negative. Just they are all positive integers. Okay? However, in many cases, a signed integer, maybe you need to put a sign that is positive or negative. Okay, we did that in the O level using the 2's complement. Okay, okay, we need so in many cases a signed integer is needed, where the coding has to identify whether the number is positive or negative. Okay, so here in the AS, we are studying it in a more general case. A number would be only positive, then we call it unsigned integer. A number would be positive and negative, and then we call it signed integer. Okay, in the O level, it used to be 2's complement. Here, you may have some additional pieces of information. So unsigned integer, like all days. If you have 8 bits unsigned integer, you have to, your weights will be 1, 2, 4, 8, 16, 32, 64, 1 to 8. An unsigned integer can be stored simply as a binary number. The only decision is the number of bytes. That is the number of bits. Whether you use 8 bits or 12 bits or a 16. Okay, the number of bits. How many bits? 8 bits, 12 bits, 16 bits. Okay. Okay, now you have to do the following. This should be very easy. To convert the unsigned number 0101, 1111, 1100 to denary. What's about it? Only thing here is that it is 12 bits. It is 12 bits. So can you remember the weights? 1, 2, 4, 8, 16, 32, 64, 1 to 8. This is only 8 bits. If you carry on, then you get 256, 512, 1024, 2048. Okay, do this yourself. Here are the weights for your reference. Okay, put the values. That is 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0. Okay, multiply and add. I am training you how to add using a pencil without using a calculator. Okay, please go ahead and do it and send me your answer. Okay, thank you so much. The correct answer is 1532. 1532. Meshi. So probably if you get anything other than this, probably you have miscalculated an addition or so. Okay? Okay, let us carry on. Then we need to talk about signed integer. Signed means positive and negative. Okay? There is one little new piece of information here. It's not so successful, is not used mainly, but I cannot omit from the syllabus. I cannot. Okay, there is something called sign and magnitude. There is one way of presenting positive and negative numbers in what is called sign and magnitude. Okay, so the idea behind this is not successful at all. I wish I can omit from the syllabus, but not now. With sign and magnitude, for example, if you have 8 bits, one of them will be a sign, which means this is the magnitude, this is the value. And if you have here 0, then this number is as it is. If you have here 1, this number is negative. This is not so successful. A better way of representing positive and negative number is using the 2's complement. A better way. However, there is something called sign and magnitude. Okay? There are a number of disadvantages using this format. A better approach is to store in 2's complement. Okay, so there aren't much discussions about the sign and magnitude. It is just there. I don't have examples about it. Let us see if we can see it in exam papers. Okay, a better way is to use the 2's complement. Okay, so you already know what a 2's complement is. Okay, however, in the AS, I also need to teach what a 1's complement is. The 1's complement of a, and this is all towards representing positive and negative numbers. Okay, you already know from the O level that you have something called 2's complement, and this is what we will be using intensively. This is what we will be using intensively. Okay, however, there is something called 1's complement, and it was on the exam last year. I need to tell it. The 1's complement of a binary number is defined as the binary number obtained if each digit is individually subtracted from 1. This is totally nonsense. Okay, this is the definition. We will talk about it later. But here it means if you need to find the 1's complement, you switch every 0 with 1 and switch every 1 with 0. If you have a number and you would like to find the ones complement of that number, you change every 1 to 0 and every 0 to 1, and that's it. Thank you so much. Why do we ever need 1's complement? I just don't like it. I like to directly find the 2's complement using the FAST method in the O level. Okay. Okay. Okay, but you can, in the AS, you may say, for example, give the 8-bit ones complement representation. This is the example. The 8 bits, and also you need to specify how many bits. The 8 bits one complement representation of the number negative 120. Okay, so you would like to represent the ones complement of negative 120. The way is that forget the negative and find the denary value of positive 120. Okay, so find the denary value of positive 120, represented like this. And the ones complement is found by replacing every one with 0 and replacing every 0 with 1. So simple. That was in last year's exam, so I need to explain it. So, okay, you can practice that with me. You can, and you do that very, very fast. So positive, okay, the binary representation of positive 120 is, okay, and as you can see, this is negative 128, because very soon I will be dealing with the 2's complement. Okay. Okay, so you represent the positive 120, that's 64 plus 32 plus 16 plus 8, that becomes 120. The ones complement is found by replacing every 1 with 0 and every 0 with 1. So it becomes, this is the ones complement representation of negative 128. You need to study it. Then we come to the 2's complement. This is the most widely used method to represent positive and negative numbers. The 2's complement is defined as the binary number obtained if 1 is added to the 1's complement. You can find the 1's complement and then add 1 to it, and this becomes the 2's complement. However, I have a fast method to find the 2's complement directly, and this is what I have been using in the O-level, because in the O-level I don't need to mention that 1's complement. So if you need to convert a binary number to its 2's complement form, you can use the method indicated by the definition, is that you first get the 1's complement and add 1 to it. However, there is a quicker method. Start at the least significant bit. So this is the fast method. ماشي? Start at the least significant bit and move left. Copy any zeros up to the first one and also copy, which is also copied. So you start from the right. If you have zeros, copy the way they are until you get the first one and copy it the way it is. And afterwards, start flipping. Any remaining bits are changed from 1 to 0 or from 0 to 1. Okay? Okay. So okay. Please go ahead. Go ahead and practice. Go ahead and practice. Okay? We have the following 2's complement integer 0, 1, 1, 0, 0, 1, 0, 1. And we'd like to convert it into denary. And this is represented in 2's complement, which means this is represented in 8 bits 2's complement, which means weights are 1, 2, 4, 8, 16, 32, 64, negative 128. Okay, so weights in 2 bits 2's complement, ماشي, in 8 bits, 2's complement. The one on the far left will be negative. The weight will be negative 128. And also, all this is in O level. And also, if you look at this and find a 0 on the far left, you can expect that this number will become a positive number, will evaluate into a positive number. Please give yourself time and convert this and send to me. So the answer is 64 plus 32 plus 4 plus 1, and this is 101. Excellent. Okay, let us get a little bit higher. So this is a denary number represented in 2's complement with a 1 on the left. A 1 on the far left. This means it's going to be a negative number. Okay, please go ahead, calculate it. Just this is straightforward. The point is you have to add 64 plus 8 plus 2, and then you add to it negative 108, or you do the opposite. You do 128 minus those and make sure that the result will be negative. Okay, just try to settle all these skills, okay, so that you can do that comfortably. Okay, give yourself. Okay, I'm seeing answers. Okay, I'm seeing answers. So it should be negative 53. The correct answer is negative 53. Please revise your work and check. Okay, excellent. So now let us go ahead. We would like to find the 2's complement of the binary number 0101 1111 1100 using the FAST method. Okay, using the FAST method. For any method, it's up to you. Okay, let me explain the FAST method first. So, starting from the right, any zeros are copied the way they are. Okay, up to the first one, which is copied as it is. And afterwards, flipping the 1 to 0 and 0 to 1. Okay, flipping any 0 to 1 and 1 to 0. Okay, look at this and study it, because I will be giving you a real exam example to solve right now. Okay, and also you may wish to do that exercise. If you convert this to denary, it will be something. After computing the 2's complement of it, it will be exactly the same value as above with a negative sign. Okay, because finding the 2's complement is just negating a number. It's just negating a number, making it negative. Okay, يا شباب? Okay, is that method clear for you? You can practice by finding the denary equivalent to this and finding the denary equivalent to that, and they will be exactly the same number except for that negative sign. Do that yourself to find confidence in what you are doing. Okay, so if your next exercise will be using 2's complement, the denary number negative 93 would be represented in 8 bits. Okay, Now we need to represent negative 93 in 8 bits. My method is as follows. You get the binary representation of positive 93. We call it the magnitude. First, we get binary equivalent of the magnitude. And here we have 8 bits. Okay? It is represented like this. 93 would be represented like this. 1 0 1 1 1 0 1. Okay, check that with me. Work on that. Check that with me. Then we get the 2's complement by the first method, which is moving left. We'll start from the right and moving left. Copy any zeros. You don't have zeros here. Copy any zeros as it is, as there aren't any zero. Copy any zeros up to the first one, which is also copied. So you copy the 1. Any remaining bits are changed from 0 to 1 and from 1 to 0. This is the fast method of finding the 2's complement, or the negative equivalent of a number. Okay? Can you take it as a homework that you do negative 77? Okay? And also do the negative 194. So you can pause my video. Okay? You start now working on negative 77, and that you get the binary representation of 8 bits magnitude of 77, and then you apply the first method and get the 2's complement. Okay? And then you check with me. And also work on negative 194. You do the 8-bit representation of positive 194. And then you apply the fast method to get the 2's complement. And then negative 239. I am putting them in ascending level of complexity. Why they would be more complex? Because you are using more bits. However, there is one little thing here. With negative 239 and negative 194, you need 12 bits to complement. It cannot fit in 8 bits. The exam is making it clear for you. You need to deal with 12 bits. So weights become up to 2048, and here negative 2048. Okay? And then next lesson, we discuss the range of integers, the smallest and the largest. Okay? And we stop here and we do that subtraction thing next lesson, inshallah. I hope everything is clear for you.